Coordinate measuring machines, or CMMs, are sophisticated tools used in manufacturing and engineering for precise measurements. These machines use a probe to touch points on a workpiece and determine its dimensions, shape, and position with high accuracy. CMMs are essential for quality control, ensuring that parts meet strict tolerances and design specifications. Unlike traditional measurement tools, CMMs offer a three-dimensional analysis of complex geometries, providing a comprehensive understanding of the object's characteristics. The applications of CMMs are vast, spanning across various industries, including automotive, aerospace, medical, and electronics. From inspecting the intricate details of an engine block to verifying the alignment of medical implants, CMMs play a crucial role in maintaining quality and precision. By providing accurate and reliable data, CMMs contribute to improved product design, reduced waste, and enhanced manufacturing processes. At the heart of a CMM system lies the touch trigger probe, a sensitive instrument that makes contact with the workpiece to record its coordinates. This precise contact is crucial for accurate measurements. These probes consist of a stylus, a slender rod-like element attached to a sensitive triggering mechanism. The stylus is often made of ruby or other hard materials to ensure durability and precision. When the stylus touches the workpiece, it triggers a signal, prompting the CMM to record the probe's precise location in space. This signal is instantaneous, ensuring that the exact point of contact is captured. This data is then used to calculate the dimensions and geometry of the measured object. The accuracy of these calculations is paramount in quality control and manufacturing processes. Touch trigger probes come in various configurations, each optimized for different measurement tasks. Some are designed for high-speed scanning, while others are tailored for high-precision measurements. Fixed probes maintain a constant orientation, suitable for measuring simple features like planes and holes. They are often used in applications where the measurement path is straightforward. Articulated probes, on the other hand, offer multiple degrees of freedom, allowing them to access complex contours and undercuts. This flexibility makes them ideal for intricate parts with challenging geometries. The choice of probe depends on the complexity of the workpiece and the specific measurement requirements. Selecting the right probe ensures optimal performance and accuracy in the measurement process. To automate the measurement process, CMMs rely on a specialized programming language that utilizes touch trigger codes. These codes are instructions that dictate how the probe interacts with the workpiece and what measurements to take. By using touch trigger codes, programmers can create measurement routines that execute a series of movements and measurements automatically, ensuring consistency and efficiency. Touch trigger codes provide a standardized way to define measurement paths, probe angles, and data collection points. They enable programmers to specify precisely how the probe approaches the workpiece, the force applied during contact, and the type of measurement to be performed. This level of control is essential for obtaining accurate and reliable measurement data, especially for complex geometries. A variety of touch trigger codes are used in CMM programming, each serving a specific purpose. These codes are essential for guiding the probe to perform precise measurements, ensuring the accuracy and reliability of the data collected. Understanding these codes is crucial for creating effective measurement routines. Without a solid grasp of these codes, the programming of the CMM could lead to errors, inefficiencies, and inaccurate measurements, which can be costly in a production environment. Some of the most common touch trigger codes include: these codes form the backbone of CMM programming, allowing for a wide range of measurements to be performed with precision and consistency. Go-to point. This code directs the probe to move to a specified coordinate in space without taking any measurements. It is a fundamental code used to navigate the probe to the starting point of a measurement sequence. It is often used to position the probe before initiating a measurement sequence. By using the go-to point code, the probe can be accurately placed at the desired location, ensuring that subsequent measurements are taken from the correct starting point. PLN plane. This code instructs the CMM to measure a plane by touching 3 or more points on its surface. The points are strategically chosen to define the plane accurately. The CMM then calculates the plane's orientation and position in space. This information is critical for understanding the flatness and alignment of the surface being measured, which can impact the overall quality of the manufactured part. CIR circle. As the name suggests, this code is used to measure circles. The probe takes multiple touches along the circumference of the circle. Allowing the CMM to determine its diameter, center point, and roundness. This is essential for parts that require precise circular dimensions, such as gears and bearings. See well, cylinder. Similar to the circle measurement, this code measures cylinders by taking touches along their curved surface. The probe follows the contour of the cylinder to gather accurate data. The CMM uses this data to calculate the cylinder's diameter, axis, and straightness. This information is vital for ensuring that cylindrical parts, such as shafts and rollers, meet the required specifications and function correctly in their intended applications. Section 5. Breaking down the syntax. A closer look. Touch trigger codes follow a specific syntax, ensuring clarity and consistency in CMM programming. This syntax is crucial for the accurate functioning of the coordinate measuring machine, or CMM, as it dictates how the machine interprets and executes measurement tasks. While the exact syntax may vary slightly depending on the CMM manufacturer and software, the general structure remains consistent. This consistency allows engineers and technicians to work across different systems with a foundational understanding of the programming language. A typical touch trigger code consists of the following elements, each playing a vital role in the overall functionality of the machine. Code. This is the abbreviation that identifies the type of measurement or action to be performed, such as GOTO, PLN, CIR, or CIL. These abbreviations are standardized to ensure that anyone familiar with CMM programming can understand the intended action. Parameters. These are numerical values or variables that provide specific instructions for the code. They define the exact details of the measurement or action, such as dimensions, coordinates, or other critical data points. For example, in a GOTO code, the parameters would be the X, Y, and Z coordinates of the target position. These coordinates guide the CMM to the precise location where the measurement is to be taken. Modifiers. Some codes may include optional modifiers that alter their behavior. These modifiers can be used to fine-tune the measurement process, adding flexibility and precision to the programming. For instance, a modifier might specify the probe angle or the number of touches required for a measurement. This allows the CMM to adapt to different measurement scenarios, ensuring accurate and reliable results every time. Section 6. Touch trigger codes in action, real-world examples. To illustrate the practical application of touch trigger codes, let's consider a few real-world examples. Measuring a hole. To measure a hole, a programmer might use a combination of GOTO and CIR codes. First, a GOTO code would position the probe near the hole's center. Then a CIR code would instruct the probe to take multiple touches along the hole's circumference, allowing the CMM to calculate its diameter and position. Inspecting a curved surface. For inspecting a curved surface, a programmer might employ a series of GOTO and point codes. The GOTO codes would guide the probe along the desired path, while the point codes would trigger measurements at specific locations, enabling the CMM to create a profile of the surface. Section 7. Troubleshooting and problem solving. Even with careful programming, issues can arise during CMM measurements. Some common problems and their solutions include probe triggering issues. If the probe is not triggering consistently, it could be due to a damaged stylus, debris on the workpiece, or incorrect probe calibration. Cleaning the probe, replacing the stylus, or recalibrating the system can often resolve these issues. Inaccurate measurements. Inaccuracies can stem from various factors such as thermal expansion, workpiece deflection, or probe deflection. Controlling the measurement environment, using appropriate probe configurations, and applying proper measurement techniques can help mitigate these errors. Section 8. Mastering CMM programming, the importance of codes. Understanding touch trigger codes is paramount for anyone involved in CMM programming and operation. These codes form the backbone of automated measurement routines, enabling precise and efficient data collection. By mastering these codes, programmers can unlock the full potential of CMMs, ensuring the production of high-quality parts and components. Section 9. Conclusion. Embracing automated precision. Touch trigger codes are essential tools in the world of precision measurement. They bridge the gap between human intent and machine action, enabling CMMs to perform complex measurement tasks with speed and accuracy. As manufacturing continues to demand tighter tolerances and intricate designs, the importance of touch trigger codes will only continue to grow, driving innovation and excellence in various industries.